So, hi everyone. Good morning. Uh, Welcome to the first session. So, now Professor David Nelson is going to present his lecture. So, over to you, sir. Just one more thing I want to say is that if you have a question, please use mic or just raise the hand.
Okay, people can hear me, I think. Well, as I was starting to say, it's a great pleasure to be at this beautiful place. It's a great pleasure to come back to India. And it's a great pleasure to see people in person and not be constantly Zooming. So what I'd like to tell you about today, I'm going to slide this over closer. Okay, I can do that. Okay, good. So what I'd like to tell you today, first of three lectures, is a story about symmetry breaking in sheet polymers, which in some sense is an old story, but it's also a new story because of the recent developments in the study of graphene. So it's a place where soft and hard condensed matter meet, and hopefully have interesting things to say to each other. So that's going to be the subject of this talk today. I welcome interruptions. I've already been impressed with the people at this school because they are not shy to stop the speakers, and I hope that you'll continue to stop me as we go along if there's anything that's not clear. Today's lecture is going to be on symmetry breaking in sheet polymers. The spectrum skeleton of red blood cells is a soft matter example, but graphene, freestanding graphene, has recently come into its own, and that'll motivate some of what I'll tell you about in a minute. My lecture tomorrow will be on a different subject. Today I'll be mostly at the blackboard. Tomorrow I'll be using PowerPoint, but hopefully in a fairly leisurely way so that you can stop me without difficulty. And I'll talk about some very recent work with Farzan Fafa and Grace Zhang and Amin Dost Mohammadi about defect emission and absorption for liquid crystals on cones. And here is one of the things we'll be talking about, actually in the context eventually of active matter. And we'll eventually have these now quite familiar +1/2 defects orbiting around the apex of the cone on occasion, and sometimes being forcibly emitted or absorbed by the singularity in the Gaussian curvature at the tip of a cone. And finally, for the lecture on Friday, I'll tell you about the statistical mechanics of mutilated sheets and shells. And this is an attempt to try to get graphene, which seems to be firmly in its flat phase, to crumple up and behave more like a sheet polymer analog of the linear polymer chains that we heard about in yesterday's very nice talk about polymer drag reduction. So that's where we're headed. And just to motivate the mostly blackboard stuff that I'll cover today, here's a cartoon of a linear polymer chain. And of course, this is the kind of entropic spring that we heard about a lot yesterday, in fact. And what I'd like you to do is to think about this as a kind of statistical mechanics problem, somewhat like the one-dimensional Heisenberg model. Classical one-dimensional Heisenberg model spins, and this one-dimensional Heisenberg model actually is intimately connected with linear polymer chains. I'll leave out self-avoidance and stuff, just keep it simple and look at an entropic chain. So you probably know that if you have a polymer wandering around, probably in 3 dimensions, might look like that. And a local order parameter, which plays the role of a Heisenberg spin, is a tangent to this polymer at arc length S. And as it wanders, probably in 3 dimensions, as in that picture, rather than in 2 dimensions, eventually it forgets where it was pointing, and it loses its memory, its orientational memory. And so like a Heisenberg spin chain with some kind of short range order in 1 dimension, we usually don't have phase transitions in 1 dimension, so there's usually a finite correlation length. This will forget its direction over some length scale, which measured along the polymer backbone is sometimes called LP. It's the persistence length. And technically, if you calculate a correlation function of a tangent at arc length S1 dotted into a tangent at arc length S2, this thing you can show will fall off exponentially fast in the separation along the backbone, where we have a persistence length like that. Standard lore in polymer science, and this is an example. How many of you have heard of the worm-like chain in polymer science? Anybody? Some hands are going up. So this is the worm-like chain. It has some stiffness. In fact, it's controlled by a bending rigidity. And so if I write down its energy, if I just take a rigid rod and bend it in various ways, since the time of Euler, people have been writing down energies which integrate along the polymer or rod backbone. If it were a microtubule, the persistence length might be very, very large. But let's assume that we have a polymer that's much larger than the persistence length. So we'll be working in the limit where L is much, much greater than this length. A model that generates this kind of physics takes the polymer position, R of S, as its basic variable. From R of S, I can, of course, get a tangent. So T of S is the derivative of R with respect to arc lengths. And then in terms of the position variable, I can rewrite this as 2 derivatives of R with respect to S. And it's an energy which, for whatever polymer configuration I have, if I rotate it, it's invariant. So it's a rotationally invariant energy. Euler got it right. And then there's this bending rigidity, kappa, this bending constant that plays a role here. And although I'm not going to derive it today, I can show people afterwards if you want, you can show that this model, which can be rewritten. Let me rewrite it first. I'll rewrite it in terms of the tangents. This is what makes it look like a continuum Heisenberg model. It can, of course, be rewritten in terms of the tangents in this way. And so it looks like a vector in 3 dimensions, pointing in 3 dimensions, but with an internal space, which is the 1-dimensional backbone. And it's well known that this problem doesn't have a phase transition. I think Michael Fisher showed that in the early 1960s. But in any event, the conclusion from this analysis of 1-dimensional statistical mechanics is that there is a persistence length, and that comes in a kind of spin-spin correlation function way. And that persistence length, at least in the limit of a very strong bending rigidity, is just kappa over kBT. And if we think of this as a temperature-dependent quantity, so focus on this temperature dependence, what that says is that there's a diverging correlation length in this one-dimensional problem. But it's a simple power law in temperature. And so there's always a finite persistence length. And in the end, I can break the polymer up into segments of order this persistence length. And then what happens is that the worm-like chain becomes the freely jointed chain. Freely jointed chain. And it's an approximation, but it makes perfect sense if you go on scales large compared to the this persistence length. And what it really is saying in the end is an important example, actually, of what in particle physics might be called spontaneous mass generation. What does that mean? Well, for scales much greater than this persistence length, then I can imagine breaking up the polymer into segments which are orientationally independent. They're each of length LP, let's say, etc. And then it's a much easier problem because there are now no interactions between segments. When we go beyond the persistence length, it's sort of a freely flopping chain or a freely jointed chain. And it turns out that there's an effective Hamiltonian. This Hamiltonian over here is transformed, and you can sort of show this almost on the back of an envelope using sort of renormalization group arguments. But there's an effective Hamiltonian, and that effective Hamiltonian is going to be J, and it's going to be basically one derivative less in dRds squared. Kind of a slightly strange result, perhaps. So this is a kind of infrared coarse-grained limit. Maybe people put a factor of a half there. In any event, I can also think of this as generating a kind of mass term in the tangents. That's actually fairly remarkable that should happen. I should emphasize that these are soft tangents, and in particular, they're a kind of coarse-grained version of what's going on here. And so I might have a coarse-grained tangent now in this new picture, and it doesn't have to be of unit length. In the original problem, the worm-like chain problem, you might typically have a very stiff polymer that still bends, and then you would have this equals to 1, but that's not going to be the case if you coarse grain and things get floppy and so forth. So you have a kind of soft tangent picture. Soft tangent. And a remarkable fact, this is, I think, kind of remarkable. You start with, there's no, you generate a mass, spontaneous mass generation, something quadratic in T that wasn't there to start with. This thing had a gradient of T. So suddenly you get this thing, and it turns out that this J, you can show, is given by KBT squared over the original bending rigidity, up to factors of order unity possibly. But that's a statement of the fact that there's no phase transition in one dimension, but you can also think of it in terms of this spontaneous mass generation. And it's almost as if you had a potential for the tangents that is sort of starts off as a kind of wine bottle potential microscopically. And then when you coarse grain and allow thermal fluctuations to act, instead of having so this is a potential in the space of the tangents. So suppose I have just two directions to make it a little easier to draw, Tx and Ty. And then as a function of the tangents, there's a preferred length in the worm-like chain model, happens to be 1. And then this becomes a parabola. And so you've lost the Goldstone mode of rotation around the bottom of this wine bottle.
David?
Yes, please.
Sorry. It's okay for people, for returning students to ask questions, I hope.
I certainly hope so. And yes.
So, no, just that in principle, in the original Hamiltonian, you actually want either a hard or a soft cost for T to deviate from unit magnitude in what you started with.
That's correct.
Yeah. So I'm saying that, yeah, I'm just saying that it's not written, but in principle, the difference between that and that is that there's actually a T dot T minus 1 whole square or something.
Yeah, you're right. So I could have taken this problem, thank you for the question, and added some kind of coupling like this, soften the tangent constraint, and put in T of S squared minus 1. And now I have a double well potential in the limit.
Whole square.
All squared. Thank you very much. Right. Exactly. So start with a model that's got this double well potential, and then we move to a situation where we have a mass that wasn't there to begin with. Well-known stuff, just reformulated slightly. So I need to get my picture back here. So I guess I presume I share the screen again here. And let me try this. And amazingly, it worked. Okay, so that's an old story. But I want to try to contrast with what happens if we talk about two-dimensional sheet polymers. And so if I can get this thing to advance, just do it manually. I don't know if we have an AV person here, but this is not advancing. There we go. Okay, so here's a sheet polymer. And that could be a piece of freestanding graphene. It could be, some of you may remember from ancient times, there was an interest in the spectrin skeleton of red blood cells, which was it's a polymerized net that gives red blood cells their shape, and you can extract them from red blood cells and do diffraction experiments and look at them. And I'm going to try to convince you that although it's a two-dimensional system, which like one dimensions is very fragile and subject to thermal fluctuations, the system nevertheless stiffens and develops long-range order in the normals at low temperatures. And indeed, there's still a controversy about whether you could actually get this thing to crumple at high temperatures. It certainly does that in computer simulations, but with self-avoidance, it's still a controversial subject. But if I have this kind of object at the top, why doesn't it form this crumpled thing to take advantage of all the entropy that we know is present in the linear polymer chains? So that's sort of where I'm trying to go here. It was figured out in the early 90s or so that objects like the sheet polymers, not to be confused with lipid bilayers, which I'll talk about probably briefly, which have liquid-like order in the plane. If there's a shear modulus, as there would be in graphene, for example, this thing, despite thermal fluctuations, manages to, although become wrinkled, and in fact, it still manages to be flat. And the analog, if you like, of the tangents perhaps is the normal to the surface. And if you think of the normals, we have a Heisenberg model in 2 dimensions. Classical Heisenberg model in 2 dimensions with 3 components is well known not to have a phase transition either. But something happens to destroy that simple expectation for these sheet polymers. And there is in fact, as I'll try to demonstrate today and maybe a little bit more overview on Friday, there's long range order in the normals in violation of the Hohenberg-Merman-Wagner theorem. Not that the theorem is wrong, it's that this system has unusual properties because of its shear modulus that gives rise to interesting science. So any questions about the roadmap? I made myself understandable. In an audience like this, if you have a question, I'll bet there are at least 5 other people who have a similar question and will be secretly grateful if you ask it. Returning students can ask, of course, as well. All right. So we can ask, well, let's start from a polymer perspective. And yes, please.
Can I,
Of course.
as you said, this sheet is 2D. So what does it mean that a 2D sheet has a shear moment?
Okay, so thank you. We'll talk more about it later, but the shear modulus of, for example, this piece of paper is what enables the sheet to have a definite shape. If it were a liquid and I were to pull on it, it would just get longer and thinner in one direction and longer in the other direction. If I pull on this, it stops. And there's a modulus called the Young's modulus that tells you the strength with which it stops. And that's proportional to the shear modulus. So anything with a shear modulus is going to be different, I'm going to try to argue, than what you would get for a lipid bilayer, which is a liquid-like membrane. Other questions? Okay, so let's take a look at this thing. Oh, let me just say one other thing. Thermal wrinkles, although they may not prevent long-range order, strengthen this wrinkled piece of paper. See, this pristine piece of paper can't even hold its own weight. Okay, and this one, no problem. In fact, people have measured the bending energy of graphene and compared it to first principles quantum density functional calculations at T equals 0. And at room temperature, the bending rigidity of graphene, 10 micron square of graphene, is 4,000 times bigger than the quantum theorists would have predicted. So there's something here perhaps to be understood.
So on what scale is this number?
10 microns. If it's 40 microns, it would be 10,000 times bigger. It is going to be scale dependent. Hooke's law is going to die in this lecture and on Friday. In an interesting way, I mean, I want to disparage Hooke. But in any event, why, let's go return now to this problem. Why don't we have something like this due to entropy? And in fact, simulations show that it does tend to crumple. It's certainly above a certain temperature, it tends to crumple. And so we'd like to understand what's going on. Why is the flat phase possible? Why don't we always get sort of a two-dimensional crumpled analog of a 1D polymer? So experiments. Well, I mentioned spectrum skeletons, but let's just talk about solid state physics here, which also interesting subject. And there are, in fact, beautiful covalent analogs of these flexible sheet polymers. And going way back in the early 1990s, Terry Hua and Toyo Tanaka and Kokufuda looked, for example, and they just made pictures of these crumpled graphene oxide sheets. This is before graphene became fashionable. It's not exactly graphene, but it's somewhat like it. Here's the rag phase of aluminum disulfide, studied by Russ Chianelli, I think it was at Exxon at the time. So it looks like a crumpled piece of paper, but maybe it's out of equilibrium. Who knows what's going on? This field got a real shot in the arm, thanks to Paul McEwen and collaborators at Cornell University. And they were able to fabricate and liberate graphene sheets. Rather than have it stuck to a substrate, just stick it to an insulator, and then you could put on leads and measure IV curves. They actually were interested in the mechanical properties. And so if you look at this thing, this is a little graphene sheet about to be liberated from its two-dimensional environment into a little bit into the third dimension. This is escape into the third dimension. This is a needle, and they're going to mechanically try to put this needle, have it dig into the graphene sheet, and you're looking at the wrinkling of an atomically thin sheet of matter. That, to my knowledge, has never been done before. It's like single molecule biophysics, but it's applied to graphene. And you can do other things, which I'll tell you about. Well, a very interesting question. You have to be very gentle, but these are strong covalent bonds. It's not necessarily a single sheet of graphene. It may be polycrystalline, but for better or for worse, you can see it recovers completely. It's a good question, of course, and a remarkable observation. So what else could you do with this graphene that would be interesting? Well, Galileo Galilei was interested in cantilevers. And this is from one of his beautiful expositions of one of the new sciences. This is the new science of mechanics, I think. And well, what about a graphene cantilever or a boron nitride cantilever? Can we make a diving board out of boron nitride or tungsten disulfide? And in fact, this seems to be in the flat phase. It's not crumpled. Here's an artist's conception of a graphene sheet attached to a gold pad that's been liberated from the substrate, has these thermal wrinkles in it, and you can measure its bending rigidity by putting a gold pad and measuring the weight, the deflection due to that weight. So that's the kind of question we might be interested in. And if you like H-bar related physics, I'll try to talk a little bit on Friday about the Dirac electrons which live in this graphene. And we can ask, what are their properties in this sort of Dirac quantum world where there's a background of fluctuating curvature, it has a mild resemblance, at least, to general relativity. It happens to be two-dimensional. There's a bending rigidity, which doesn't happen in relativity, but there's this fluctuating background, and electrons have to live and move around in this environment. People are beginning to look at that, but there's a lot of unsolved problems there as well. So I'm sort of motivating, looking at these things. Oh, this is a graphene spring, excuse me. They cut a whole bunch of holes in it. You can do 10,000 pulls, atomically thin. And notice when you pull it, you could sort of see it. It's escaping into the third dimension. It's twisting. The third dimension is going to be important once you have freestanding graphene, as opposed to just gluing it to a substrate. Any questions about? Yes, but
the black line that kind of shape.
okay.
Are just ondulations of the surface.
So which black line are you referring to? This is a gold pad here.
Yes, that's
Okay, and this is a little needle that's stabbed into the gold pad, and then this is a corrugated.
the corrugation, the black line that is.
Oh yeah, so I think that's a fact. And there are holes in the graphene,
Yes.
and then as it pulls and goes out of focus into the third dimension, I think the optics produces something that looks like a black line. Thank you. The projection of these strands gets thinner as it twists. It was created by a laser ablation, and they made it periodic. So they just made it.
Artificial. It's not just the graphene that produces this.
That's right. So they made graphene. That's right. In fact, before they took it off the substrate, thank you for the question, they made a periodic lattice of holes with a laser, and then they made this exquisite atomically thin spring. Never been done. Yes, the individual strands of the spring are twisting, and in fact, I don't have an example here, but if you take like cut a picture frame out of a piece of paper and pull on the corners, it will twist and escape into the third dimension, trading stretching energy for bending energy. So that's what's happening, but it's happening on something which is 2 angstroms thick. Yes, please. It's in water. Thank you. The question was, is this suspended? It's freely suspended. It's in water. There's some surfactant that keeps the graphene from sticking to itself, and it's being done at room temperature. Other questions? Yes, please.
Let's say you are compressing the seats up to certain extent and you are again retracting.
Right, right.
Yeah. But if you go beyond that,
Yep.
but is it something buckling kind of things will happen? Because we are limited to that so that we can go beyond the buckling regime.
Well, so thank you. It buckles almost immediately as you start pulling it. At least it twists into the third dimension, and there is a buckling transition almost immediately. I don't know if you pull even harder, could you get it to break or fracture? That's a separate problem. But the strain with these holes is like 250%. So it's an amazingly flexible thing, and it comes back, and it comes back. They can do it thousands of times. Other questions? Okay, so I think that's what most of what I want here. Yeah, so we'll skip that for now. Do this. Okay, so do this, in fact. Please.
Hooke's law.
Yes.
Mentioned Hooke's law is going to die.
It's going to die.
So
It's very sad.
It's already dead in this picture.
There are experiments that I'll describe that on Friday that will describe the death in detail.
Not here.
Not yet, right?
Thank you.
Okay, so let's see if we can't come up with some theory of this problem involving the tangents and involving soft tangents, which might have a double well potential and so forth, as Sriram was mentioning. So, you know, if natural variables to look at here are in fact the tangents. So what I'm going to do is Landau theory in the tangents. To a sheet polymer. So our sheet polymer, imagine it's ruled, as graphene surely is ruled by it having a regular honeycomb lattice of atoms. This wonderful piece of graph paper, thank you, Ranjini, for the paper, is ruled as well. And as a function of the internal coordinates of this graph paper, which I'll call X1 and X2, we have some kind of polymer configuration in 3 dimensions. So this thing is in R3. And now the natural quantities to look at are a pair of tangents, T alpha, which are the partial derivatives of R with respect to X alpha. And alpha runs over 1 and 2. And if the thing is crumpled, like a linear polymer, we could imagine that the tangents are kind of soft. And we can start by saying, well, let's assume that the tangents are small. So in a crumpled phase, if there is one, assume a crumpled phase has small tangents. And we can do a Landau kind of expansion in the tangents, much like what I did for this linear polymer here. And the particular Landau thing, which I'm not going to go through all the details. I apologize to the students if you got this chapter from a book that Grace Zhang and I are writing late last night, and you didn't get much sleep if you were looking at it. I apologize for that. But in any event, the details are in there. And this Landau expansion is a functional on X1 and R of X1 and X2. And it's going to look something like the following. We already saw for linear polymer chains, there's a term which involves two derivatives of R with respect to its internal coordinate. In this case, X1 and X2, there are two of them. So there's a summation convention summing over the alphas here. And now here comes an expansion in the tangents, okay? So I'll rewrite it. I'll write it in terms of R, but we could also equally well write it in terms of tangents. There'll be a term like that. There'll be a, now I go out to quartic order in these tangents, and I'll have d alpha R, d beta R squared, again with the summation convention. And then there's another thing I can write, which has also was rotationally invariant. It has to be rotationally invariant both in the three-dimensional embedding space and in the internal space. If it's has a high symmetry like graphene, it's not going to depend on a rotation of if I were to reparameterize things and do a rotation operation on X1 and X2, a rotation by an angle theta, this is invariant under that rotation, also invariant under a three-dimensional rotation, plus dot, dot, dot. And now we have to ask ourselves what's going on here. So if it's crumpled, then tangents are small, and you might think I could neglect these higher order terms, because see what I have here. I mean, I can also rewrite this in terms of the tangents, right? This is just T alpha squared, some alpha equals 1 to 2. And this is quartic in the tangents. There are two quartic terms in the tangents, in fact. So we can look at this problem, and let's just look at this polynomial piece for now. And let's assume, following Landau, that A, this coefficient here, is A prime times T minus TC. TC will be a crumpling transition. So if I'm above TC, this is positive, and to a first approximation, I can neglect this quartic term, then I have this, it's just like the spontaneous mass generation in a linear polymer chain. And this is some higher derivative of the tangent, so I might neglect that. And then I would have an interesting description of a crumpled, an entropically crumpled piece of paper. But I can also ask what happens at low temperature, and what happens in particular if this Landau coefficient changes sign. And so this polynomial part here, rewrite it in terms of the tangents, is 1/2 A times summation over these T alphas. That's this term here. And then I have another term, which is E, and I'll write out the sum explicitly just to make sure that we're all on the same wavelength. And then there's another quartic coupling, as I've discussed, which is a sum over gamma of T sub gamma dotted into T sub gamma, all squared. Okay, these are sums 1 to 2, the internal tangents. So the order parameter here isn't, it's an orthonormal or orthogonal dyad order parameter. So if there's a flat phase, you can imagine that there's a flat phase here, which might look like that wrinkled piece of paper a little bit. And embedded in the wrinkled piece of paper, which is on average flat, despite the thermal fluctuations, you could imagine putting to a reference coordinate system that's parallel to these tangents. I'll call it E1 and E2. So it's just kind of standard question, please.
So can you just tell us a little bit more about this crumpling transition? What kind of a transition is it? The order of the transition?
Okay,
Or-
this sort of the mean field verge theory of this would be a second order phase transition. And you could ask, what is the order parameter of this thing? And so maybe I'll answer it over here. So it's a second order phase transition, has a big specific heat singularity in computer simulations. But the simulations that are most reliable don't yet have self-avoidance. There's a separate question about what happens with self-avoidance, and that's another lecture. But for now, let's leave out self-avoidance and have a phantom membrane, and still quite interesting problem, has a crumpling transition, I think. And I'll show you how to describe it in terms of an order parameter. So for A negative, we can say that there will be a kind of an average position of this wrinkled sheet. And I will write it in the following way. I'll write it as a X1 and X2 running over weighting these two unit vectors. And the order parameter, Ranjini, is I'll call it M. It's out in front of this object, of this dyad thing. And what does it mean physically? If I start with a pristine sheet at T equals 0, and I go to finite temperatures, so this is T equals 0. It wrinkles, but still remains flat. It's going to look like this. It's going to be shrunken by the thermal fluctuations. And this M, which is going to tell us by what fraction it's shrunk. So M will, so if the original system is L by L, this M will be some temperature dependent number less than L. And it's 0 in the crumpled phase to a good approximation. So if I plot this thing, further answer your question, if I plot M of T divided by L, let's say, limit of a large system as a function of temperature, according to this Landau theory, there's an M divided by L, this normalized shrinkage factor that goes to 0 at TC. So that's the essence of the crumpling transition. And in fact, if you make this ansatz here, and just ignore the fluctuations and minimize the polynomial part of this, this energy. So if we minimize this, I'll leave it as an exercise to the students to show that in fact, M in true Landau fashion is 1/2 times the square root of minus A over B plus 2C. So B and C are, like the chordic terms in a normal Landau theory, we assume they're not strongly temperature dependent. And this would produce a prediction at the transition, the crumpling transition, where it's proportional to the square root of T minus TC.
Question, David?
Yes, please.
You have R is proportional, is sort of linearly varying with X1 and X2, right?
Yes.
So then on a scale L, anyway, X1 and X2 themselves will extend from, let us say, 0 to L or minus L to L or something. Like that,
X1
right?
and X2 go from 0 to L, you have to say.
So then does M itself further scale as L, or should be an order 1 quantity with your definition?
Okay. Yeah, it should be an order 1 quantity. Thank you for catching that. So I made a need to correct something, thanks to your observation. This goes from 0 to L, and M
Okay, thanks.
order 1. Thank you. I made an error. Thank you. Other comments? Yes, please. You can do that, and you know, you can take a microscopic model and try to figure out what A's and the B's are from a more microscopic model, but then you probably also want to put in fluctuations and that sort of thing, which I'll describe briefly. Other questions? Well, okay, so
10 micron scrap of graphene.
okay. Well, okay, so for graphene, you put in reasonable numbers for the crumpling transition. Turns out, you do the more microscopic picture, it's a great question. The more microscopic picture says that KBTC is of order the bending rigidity. All right, and so if you look up the bending rigidity for graphene, the 0 temperature bending rigidity now, not the scale dependent one that I'll come to. If you put in this 0 temperature thing, the crumpling transition for graphene is 15,000 degrees Kelvin. So good luck getting it to crumple. The bonds will fall apart. But I'm going to try to argue on Friday that if you punch a periodic array of holes in it, much like that graphene spring, you'll weaken it. You'll knock down the bending rigidity and maybe get a crumpling transition at 900 degrees or 600 degrees Kelvin. It's a great question.
But there's you don't need system scale in this. This has a good thermodynamic limit.
This has remarkably a good thermodynamic limit. And in particular, in the thermodynamic limit, it actually has a real well-defined flat phase, which was quite a surprise, at least to me. Other questions? Okay, and Ranjini, I'm going to 10:30. Is that about right? Okay, good. We're fine. We're on track here. So now let's go into this flat phase and take the next step. I mean, I could have done very similar things for a Landau theory of the tangents to a linear polymer chain. And then I would have to look at and assume, I could assume a broken symmetry state for a linear polymer chain. I would put in thermal fluctuations. I would discover, even for a worm-like chain with some stiffness, that there's a finite persistence length, and the ordered phase of a linear polymer would die. We have to decide whether that's going to happen here. So let me clear the board here. And I'll just indicate how we can go after that question for a flexible sheet polymer that has a shear modulus. Okay, so we have a within Landau theory anyway, we have an assumed flat phase, and I'm going to now assume we're low temperatures, and so for T less than Tc, you can rewrite that free energy in the following suggestive way. You can you can subtract a constant part and integrate over these internal degrees of freedom, x1 and x2. I had this bending rigidity, and I think I'm going to call it kappa tilde, because it's going to be closely related to the other bending rigidities that we're used to, but I'll call it kappa tilde for now. So here's basically two derivatives of R, but it's also one derivative of a tangent, of course. And so, yeah, here I have a kappa tilde as well. That's just that term over there. And now I'm going to reorganize this Landau theory in a hopefully suggestive way. I'm going to rewrite it like this. You can check that this is just up to a constant, entirely equivalent to what we had before, and it's very much what Sriram wanted me to write for the polymer problem in terms of the soft tangents. M, remember, is this order parameter. M squared is minus A over 4B plus 2C. So I'm just rewriting this thing, but this is sort of looking maybe vaguely familiar if you know some differential geometry. And in particular, if I have this somewhat wrinkled sheet like that, and I want to know a little, what's going on with an element of length within the sheet embedded in 3 dimensions, associated with little changes in x1 and x2, that by the chain rule looks like this. Are differentiated with respect to x1, differentiated with respect to x2, dx2. And now this length element, d squared s, which is corresponding length inside of this sheet polymer, embedded in 3 dimensions, you can check, it's just going to be summation over alpha and beta, this dot product x alpha x beta dx alpha dx beta, or using a summation convention, this is g alpha beta dx alpha dx beta. And this is nothing more than the metric tensor that you have in the presence of the thermal fluctuations. And what this Landau theory is trying to do, instead of having a tangent that might be close to 1, it is a preferred metric tensor, which is going to be flat with an m squared prefactor that counts for the shrinkage when you have the thermal fluctuations. So that's what's going on. This is a metric tensor. And we have a dynamical fluctuating metric tensor here that undergoes a dramatic change at the crumpling transition. We're going to be still looking at low temperatures, and all we have to look at is the Goldstone modes of this problem, just like we looked at the Goldstone modes of the tangent to a polymer chain. And so I'm going to leave out some details, but here are what are the Goldstone modes? The Goldstone modes are, take this crumpled sheet of paper, it's at finite temperature, and we'll imagine doing some kind of translation, symmetry, maybe rotations and stuff. We want to see what are the low energy excitations. And then we could imagine a translation that is actually weakly space dependent. What's that going to produce? Right, to do a weakly space dependent translation of an elastic solid? Phonons. Phonons are going to now fluctuate and change what's going on locally with this metric tensor. So we want Goldstone modes. And we're going to parameterize this thing by saying, okay, we had this nice representation in terms of M. And we wrote it initially as mx1, and then that multiplied this unit vector E1. Okay, that's what we had before, and we also had another term which was m times x2, and that multiplied a unit vector E2. Let's look at the phonon. Let's allow for phonon deviations here, and so there'll be a U1, which depends on x1 and x2 here. This is just we're flat. This would be a natural in-plane distortion, just like the phonons that you would have for Debye theory of the specific heat of a solid. And a similar kind of distortion here, where let's put a plus here as well, that allows the actual position to distort, just like a rubber sheet would distort. If this is constant, nothing's going to change. It's just rigid translation in the E1, E2, the plane spanned by E1 and E2. But now it can escape into the third dimension. So I'll add an E3 here, make it also proportional to M, and then there'll be a very important flexural phonon field. These are the out of plane phonon field. And professional graphene theorists have had a lot of fun quantizing the flexural graphene phonon field and seeing what its behavior is and so forth. We'll be operating on a classical level here, but here's this flexural phonon, and these are the conventional in-plane phonons. And this is, of course, escape into the third dimension, a very simple way of exploring that. And maybe if it wants to wrinkle, it's going to have these flexural phonons, and we have to see how they might change things. So that's just it's a relatively tedious but relatively straightforward exercise to take this ansatz here. And just stuff it into this free energy here, and expand in the small gradients of U and F, etc. A blizzard of algebra ensues. But if you keep calm and keep your wits about you, you can show the following. In particular, we need the metric. What is the distortion in the metric if I add in these phonons? Okay, you can show that this thing is m squared times the diagonal flat metric associated with mean field theory, but then there'll be a deviation, which I'll call U alpha beta. This is going to be a strain matrix, as you'll see. And I leave it as an exercise to the students to work out what U alpha beta is. You'll get the textbook answer for flat space. Which is the symmetrized derivative, symmetrized strain tensor here. But if you allow the escape in the third dimension, there's an additional term, which is 1/2 f x alpha df dx alpha times df dx beta. Plus higher order terms. This is where the algebra becomes painful, but the higher order terms are typically higher order in the in-plane strain. So if you keep this term here, it's okay to keep, you can throw this one away. We don't know what this one's going to do. Yes, F is nothing more than the out of plane displacement. It multiplies, thank you. It multiplies E3 here, and I should have said E3. Thank you for the question. is the cross product of this orthonormal dyad. They will, as you'll see in about 2 minutes. They do talk. There's a lowest order theory where they're independent, but in general they will talk, and they will talk in a very important way. It's a great question. They are massless, and indeed, absolutely. Okay, so then the other thing that's useful here that we would need is this second derivative. These second derivative terms in the original energy here, and that turns out to be after the blizzard of algebra. Laplacian of f squared, that's going to look like a bending rigidity when we're all done. And then there are corrections here, which can also be neglected in the limit of small strain. They involve two derivatives with respect to of f with respect to x alpha, two derivatives with respect to u beta, multiplied by two derivatives of u beta. You can check me on this, but again, this can be neglected compared to the terms I've kept. So the bottom line, which I guess I'll write over here, is a theory that is going to have the interesting new physics of sheet polymers, which is up to a constant, there's a free energy in this Goldstone way of looking at things, which has a bending term, and it turns out that this kappa is just kappa tilde, the one I started with, times m squared, the magnitude of the order parameter that I had. And lo and behold, you get the in-plane strain matrix. I'll be able to answer the question about how they talk to each other momentarily. Be a term like this, U gamma gamma. But don't forget that this U alpha beta is the usual strain matrix that you might have encountered in a solid state physics course or a mechanics course, plus this out of plane displacement. And to answer your question, when I put this in here and I square, I get a coupling between the in-plane phonons and the out-of-plane phonons. Why does that come about? Physically, it comes about because if I have, a bunch of balls and springs, and I push this ball up, the springs get longer by Pythagoras' theorem, and there's a stretching energy associated with this vertical displacement F. So this is stretching here. And it competes with this bending energy here. Okay, so the in-plane phonons will talk to the flexural phonons in a non-trivial way. All right, so let me pause here and sort of maybe reflect mildly on what we've managed to show. We attempt to share the screen again. Let's see here. Okay, so I'm going to go forward. You are sharing screen. Well, thank you for telling me that. There we go. Good. So I don't know if it's obvious, but this is a lot like a superconductor. How many of you are familiar with the Ginsburg-Landau theory, the phenomenological theory of superconductivity that leads to type 2 superconductors and type 1 superconductors? Not so many, perhaps, especially in an audience of soft matter people, so I won't spend a lot of time on it. But Ginsburg and Landau, and Ginsburg eventually, that was the source of, I think, of his Nobel Prize, wrote down in terms of a complex order parameter psi, an energy for superconducting electrons, but it has this Landau structure with the absolute value of psi squared, absolute value of psi to the fourth, and it had a coupling of the condensate wave function of the Cooper pairs to a vector potential due to, in this case, a magnetic field. And you can minimize this thing just as we minimized our little Landau theory, and find that the polynomial part of this is minimized when psi 0 is equal to the square root of minus r over 4u. And now the analog of looking for Goldstone modes is to say, well, this order parameter is like an amplitude that's determined by this thing here times a slowly varying phase function. So that's the analog of phonons, phonon displacements. A rigid rotation will not change this energy. It's a little more different in the sense that this this vector potential gives rise to a magnetic field that is the curl of A squared. But it looks a lot like our problem, especially if I make this substitution, because if I look at this thing, I get the gradient of a phase. That's like the symmetrized derivative of the in-plane phonons, with something subtracted off of it. In this case, it's the actual vector potential whose curl gives the magnetic field. Here I have something added, but it could equally well be subtracted if I change conventions. And what we have here in our problem is a kind of matrix vector potential, A alpha beta. And so, there's this little table. This is superconducting theta. The phase is like the in-plane phonon field. The vector potential is this matrix thing that I've been talking about. Well, in superconductivity, you calculate the curl of the vector potential to get a magnetic field. Turns out, if you do a similar calculation for this strain thing that gets squared, you'll get the determinant of this symmetrized derivative, matrix of derivatives of f, which is nothing more than the Gaussian curvature. So the Gaussian curvature of this wrinkled sheet plays the role of a local fluctuating magnetic field. And finally, we had derivatives of the vector potential here in our Ginzburg-Landau energy. The bending rigidity term here is not a curl per se, but it has a similar flavor. It's a derivative acting on the df dx. So it's sort of like this term here. And so there's a helpful analogy as we go forward between superconductivity and these kinds of elasticity problems. Yes, please. It's not absolutely right. It's not exactly a gauge field because you cannot make. It's not a local gauge transformation that you can easily make here. But it has the same has some similarity in the sense that there's an offset here. And in particular, it's like a gauge problem because it introduces geometrical frustration into the problem. You can never make, if you ask what's going to minimize this thing, you might say, oh, I'll try to make this thing equal to 0. If I try to make one of these things equal to 0. And okay, well, I can do that by just letting this piece equal to 0. And I'll put a question mark there because like some gauge problems, it's not a true local symmetry, you're right. It does have a similarity in that there's geometrical frustration embedded here. And this vector potential, it's a symmetric 2x2 matrix, has 3 independent components. There's only 2 components to the phonon field. You can't make it 0 in general. And so it's not a perfect analogy, but it can be a helpful guide. Other comments or questions? Uh, well, the Meissner effect, an analog of the Meissner effect would be if you take your sheet and you try to wrap it, say, around the sphere, and you're trying to put a uniform Gaussian curvature onto the system. So it's a great question. And if the sheet resists and says, no, I want to be flat, it's expelling the Gaussian curvature. So that would be an analog there. Okay, well, in the remaining 20 minutes, I want to talk a little bit about how you can get some insight into what's going on here. And this is where the 38 pages of notes that I inflicted on the students last night, again, my apologies, have details. But the answer, I think, is revealing. Let me start doing that. If you look at that free energy on the left blackboard over there for our elastic sheet fluctuating around its flat phase, a little bit into the third dimension with these flexural phonons. If you look at this thing, it's actually simpler than it seems, because when I square out these U alpha betas, I'm going to get quartic nonlinearities and other nonlinearities in the Fs. So that's a complicated problem. But it's only quadratic in U1 and U2. And so I'll put an exclamation point there. And so what do we want to do? We want to calculate partition functions and correlation functions and stuff like that. And so that can be thought of as a kind of functional integral over these in-plane phonons, a functional integral over the F at degrees of freedom of e to the minus this free energy over kBt. That would be the partition function, and closely related would be various correlation functions. This is the kind of thing we want to calculate in statistical mechanics. But it's only quadratic in U1 and U2. And so I can actually take this functional integral over the in-plane phonons, and we can integrate out U1 and U2 exactly. Integrate out U1 and U2 exactly. Therein lies 2 pages of algebra, which are in the notes that was hopefully shared with the students. The answer is more important than the actual details, but if we integrate out the in-plane phonons, it's the flexural phonons that will be left over. Those are going to be the nonlinear things that give rise to new physics. So integrate out U1 and U2. And just like we got that effective Hamiltonian for linear polymers at the beginning, there'll be an effective free energy. Still, there'll be a functional integral that we have to do. And this effective free energy turns out to be a constant. Plus, we still have bending energy, known to many soft matter people, of course, but also relevant in this context. The bending energy, that's still there. And then the result of the integration is a very strange quartic coupling constant that depends on the Young's modulus of the system, which is 4 mu plus lambda over 2 mu plus lambda. The Young's modulus gives you the restoring force on a elastic medium if you pull on it. Of course, if it has wrinkles, you might imagine that it would soften the Young's modulus a little bit, and that will actually come back probably in the lecture on Friday. In any event, in addition to this thing involving the bending rigidity, we get the Young's modulus divided by 8, I think, and then an integral d2x of the transverse projection operator acting on dfIF, dfJF squared, or the transverse projection operator, easiest to define in Fourier space, but sometimes you write it like this. So that's what's left over when we integrate out these flexural phonons. Now we have to figure out what it means. Yes, please. Is there an assumption of the connectivity of the sheet? Oh, no, it's not inextensible. It would be if I, this mu plus lambda is the bulk modulus. And so if I took y to infinity, I can make it inextensible. But this could be a soft sheet, in fact.
So why does the projector come then? Is there
It comes for good physical reasons, which I'll tell you about. Mathematically, it comes when you carefully do this integration, and the subtlety that gives rise to this basically comes because when I integrate out the in-plane phonons, there's actually 2 in-plane phonon degrees of freedom, usually that are at usual ones that are spatially variable, spatially varying, but there's 3 components of the macroscopic strain. That's a subtlety of 2D elasticity theory that plays an important role here when you integrate things out. And you do that carefully, and right now you'll have to take my word for it that you get this transverse projector, basically for the reason that I told you. But let me tell you what it means physically. Well, let's just try to at least make it plausible. All right. So if I just look at what's going on here, what are these derivatives? dFi of f, sorry, d by di, d by the xi of f, d by the xj of f. Those are the tipping vectors of the normals, okay? Those are the tipping vectors of the normals. And there's 2 kinds of tipping that I could have of the normals. There's longitudinal, if you like, a longitudinal phonon of the normal. A longitudinal mode of the normal looks like that. That's just the surface bending. That's fine. But if I go instead like this, I have to tear the surface. And so what this is telling us about is something about energy costs for tipping these normals. And there's longitudinal mode, which is low energy, and that's going to be controlled by this bending rigidity. But as soon as I start to do this, it knows it has an elastic constant, and you won't actually tear it, but you're going to have a huge energy cost. And this transverse projection operator kicks in an extra penalty when you have these transverse phonons, and that penalty is proportional to the Young's modulus. That's where it comes from. So suppose we didn't have this. Suppose we temporarily, we just say, okay, Young's modulus and the shear modulus are 0. So what happens? Temporarily get rid of this. Let's do a little calculation and see whether there really is long-range order in the normals. And our little calculation is a calculation appropriate to a liquid membrane. It's like I have it here somewhere, probably here. So we're going to basically assume that we have a liquid.
Small question, David.
Yes, please.
So you're setting only mu to 0, you're retaining lambda, so you somehow still have a displacement field, but one without a cost for shear. Is that right?
Well, depends on what stage I do it. I've integrated out the in-plane phonons already, so I've taken it into account. And having done that, I set mu equals to 0, and then this still goes away. But yeah, it's going to be I'm going to basically create a liquid. I'm going to create a liquid.
So I should think of it as just a liquid. You only have bending energy. Forget the in-plane displacement field.
Yeah, and this is how they go away gracefully.
Right.
If you integrate them out and then you let mu equal 0.
Okay.
That's a great question. So let's take a look at these so-called liquid membranes. Standard calculation goes back a long way. Has to do with it describes lipid bilayers pretty well. And so we have a free energy, which is just kappa over 2. Gaussian. And let's just calculate the normal. Is there a non-zero average of the normal? And so we'll parameterize our surface as x1, x2, r. F will be our flexural. We still have sort of flexural phonons, if you like, with a liquid membrane. So we have this thing here. The tangent T1 is equal to dr dx1, 1, 0, df dx1. The other tangent is 0, 1, df dx2. And let's just look at the normal. Let's just see if there's a non-zero average to the normal. And that seems like a pretty straightforward question to ask. So we're going to look at the unit normal for this surface. This is where I will begin to finish up. And if you work it out, so it's a unit normal, so it's going to be T1 cross T2 divided by its magnitude, makes it a unit normal. This just ends up being 1 over the square root of 1 plus the gradient of f squared, and then minus df dx1 minus df dx2, etc. And let's assume that this wrinkled surface is trying to, liquid surface now, is trying to have a normal which on average is in the z direction. So in fact, let's look at n hat dot E3, the projection of this normal. Well, that's the cosine of the angle that the normal makes with respect to the average broken symmetry flat phase direction. So, and we'll calculate a thermodynamic average of that. Are the fluctuations going to take this normal and crumple it up? That's the question here. And on the other hand, here I have explicitly the normal. This is an angle, but if I take the third component, then I have to calculate the average of 1 over square root of 1 plus the gradient of f squared. And let's assume that we'll get a contradiction, but we'll assume that at low temperatures there's long range order. So theta is very close to 0. And so we're going to assume theta and correspondingly the grad f are small. And then just expand in theta, expand in grad f, and you get 1 minus theta squared over 2. Average is approximately 1 minus 1/2 grad f squared. So we can read off the fluctuations in the tipping angle. Fluctuations in the tipping angle are going to be given by the average of grad F squared. And now, this is a job for the magic of Fourier transformation, because our Hamiltonian is in this liquid approximation, is quadratic in the F. And I leave it as an exercise to the students. It's just applying the equipartition theorem in Fourier space to this problem to show that this thing is going to be KBT over kappa times an integral d2q. Keep track of various 2 pi's. There's a 2 pi here. There's a 1 over kappa q to the 4th, because I have a Laplacian of f here, but I have a gradient here, so there's a q squared. And this is one of these famous Merman-Wagner-Hohenberg-like integrals, which diverges in 2 dimensions. If I just look at this thing and estimate it, this thing is something like ABT over 2 pi kappa times the logarithm of the size of my membrane. And this goes to infinity. As the system gets bigger and bigger, so the angle that was supposedly small fluctuating quantity gets logarithmically divergent as things get bigger and bigger. And it's pretty much agreed now, I think, that liquid membranes would, if large enough system, actually crumple. They don't in vesicles. The vesicles aren't big enough, just a logarithm, but technically there's no long range order. And I'll conclude, I only have 2 or 3 minutes, by just telling you what happens if you reinstate this coupling constant here, this Young's modulus, and redo the theory. This is what I'll talk about on Friday. But if you redo this theory with this extra nonlinear term, this is basically a massless field theory. It's massless in the sense that gradient of f is like the tipping vector. So here I have a gradient of an angle. This is an interaction between angles. It's automatically at a critical point. And so you don't have to adjust anything. It's self-organized criticality, if you like. But if you repeat this calculation for a membrane with a shear modulus, mu and y not equal to 0, what you've discovered, this is something I did many years ago with Luca Politi, and then it was done more accurately with renormalization groups and stuff like that. What you discover is that this angle ends up looking, the fluctuations in it look very much like what I wrote for the liquid membrane. But in fact, what you have is a KBT out here. There's a Q squared. There's a kappa Q to the 4th. Right now, it just looks like a liquid. This thing would be diverging. But in fact, there's a scale-dependent elastic constant that comes in now. A scale-dependent bending rigidity. And this scale-dependent, it's a renormalized bending rigidity, goes like, as Q goes to 0, it goes like 1 over Q to the eta, where eta is some fairly large critical exponent. It's about 4/5. That's a result of renormalization group calculations and some hard work and stuff like that. But the bottom line is this thing is getting stiffer and stiffer as the wave vector goes to 0, and it makes this thing finite. And so the flat phase with the shear modulus present is saved by this scale-dependent elastic constant. And that Q dependence is closely related to what I said earlier in this lecture about the bending rigidity of graphene, 10 micron square has a bending rigidity which is 3,000 times bigger than it should be. It was 20 micron squared. Sorry? It's true. There's an ultraviolet problem, but we're doing condensed matter, soft condensed matter physics here. So we never take Q to infinity.
Okay.
There's always a cutoff associated with the spacing between the atoms. So no ultraviolet problems. It's the infrared problem that we're trying to solve here. Thank you, though. That's all I have to say today. Thank you very much for your questions.
Thank you. So questions? Yes.
Hello. Yeah. So this non-isometric bending term, the with Young's modulus,
Yep.
you got when you took mu equal to 0 after integrating out in plane phonon modes.
For a liquid membrane, that's what I got. I didn't have to do that. I could have set mu equal to 0 from the beginning. You get the same answer. But what I'm talking about now is what happens when you put it back. When you put it back, there's mode couplings between the tipping angles that are associated with elastic deformations of little plaquettes of this membrane. And it gives rise to this remarkable stiffening, which in fact is closely related to what I showed you. This piece of paper is stiffer than you would have expected in the absence of the wrinkles, which are kind of a proxy for thermal fluctuation.
So you're saying that if you took mu equal to 0 in your original free energy and then integrated out phonon modes, you would have gotten the same.
Yes.
Okay.
Yes. That's a good question. But yes, you will get the same thing. Other questions?
Would you see a flat face if you did not have a bending rigidity?
Well, it's an interesting question because in the early days of string theory, people would often use Reggie calculus, triangulated membranes, and so forth. And if you just set the bending rigidity to 0, I don't think you get a flat phase, because what happens is you get wild fluctuations. The escape into the third dimension becomes uncontrollable. Any physical system in condensed matter physics that I'm aware of would have a bending rigidity. So if you got rid of it, I think you'd get branching and trees, tree-like surfaces, and so forth, like the bark of a tree. So you probably wouldn't get it, but I don't know how to make it in a laboratory, terrestrial laboratory anyway.
David, in your old papers on self-voiding surfaces, you had a kind of Flory argument for the two-dimensional case, if I remember right? So that is that self-voidance is important.
Yes, that's right.
Bending was important. You kind of forgot the in-plane elasticity, except in the back of your mind, it was tethered. I mean, right? So what happened to that state? Is that? Well,
it's still controversial. That is the crumpled state, where you sort of, the elasticity is in the back of your mind, as you say, but the tangents are really, really tiny when you coarse grain. So, what we found with like Maron Kardar and stuff was that you turn on self-avoidance in this crumpled state and it swells. But it seems to, in the calculations, it seems to swell in a fairly controllable way, and you'll get some analog of a Flory exponent for the radius of gyration. It's still a unsettled issue whether it always has to be flat. There are simulators who firmly believe that. I don't agree with them in the following sense. If I took a membrane and I had a strongly attractive Leonard-Jones pair potential between distant pieces of the membrane, it will make a compact phase. With the self-avoidance, it'll have fractal dimension 3. And then, of course, if the flat phase, which people agree is there, has fractal dimension 2. And it's very hard to rule out something in between as you tune parameters. So I think the jury is still out. I'm somewhat bruised by my interactions with simulators who looked and failed to find the hexatic phase, which is also intermediate. They seem to be finding that now. They may or may not find this crumpled phase, but that argument, you can certainly get, it's like going below the theta point of a conventional polymer. Then it becomes a solid, compact object folded in some beautiful way that does respect self-avoidance. And so I don't see any reason why there couldn't be an intermediate phase. And hopefully we'll know before too long. It's controversial.
If you had the material that, if I may ask, if you had the right material that you could actually get into the high temperature phase you were discussing,
Yes.
is it, you think you could tune through this transition in a different way rather than temperature with tension?
Yes.
Would you see?
Yeah. I
some of
think
the statistical physics?
I think you could put tension on the edges, perhaps. I heard a beautiful talk by Ramanujan at the Newton Institute in July, and he's found a way, I think, to make active sheets, sheets of active matter, that in his beautiful experiments look like they're in the flat phase. But having done that, you could imagine chemically playing around with screening and salt concentration, and maybe you could see it there. But then I think it's an active thing. So there's motors and there's microtubules, and it's quite a beautiful, I think it was talk that I'm remembering from early July.
But just with the regular passive sheet, you think boundary tension can do this? You don't need things inside the sheet to.
Well, okay. So there's two things. There's boundary tension and then there's boundary compression. Okay. So, and I think both would be fascinating to study. Boundary tension is like putting an ordering field on the Heisenberg model. It's you put a tension in various directions. And then Suraj Shankar and I have studied what happens in an ensemble where you have boundary tension. And there's a buckling transition that can be controlled by this boundary tension. And if it's inward tension, the flat phase can buckle. Whether that's the same as the crumpling transition is a dubious assertion. I might have guessed that, but I'm not sure that's the case. But putting on boundary tensions or spreading these flexible membranes across a hole of a variable aperture, like the aperture of a camera. You vary the size of the hole.
You'd like to fix M.
Yes. Yeah. So in fact, because this is a problem at a critical point, different ensembles are not equivalent. We're used to thinking, oh, it doesn't matter whether it's constant volume or constant pressure in the thermodynamic limit. But since you have fluctuations on all length scales, this is something that Suraj Shankar and I looked into. The constant M ensemble is not the same as the constant stress ensemble. They have different critical exponents. But I think it's a very active, interesting area to look at.
Okay, so further questions can be asked during the coffee break, because we also have to see the posters.